Hmm. Yeah, I'm good, baby. Ask me questions if you have any. I'm just getting some stuff ready for class. Got another one in. Hey, Dylan, did you finish your test already?
They sent me back saying that it wasn't open until tomorrow, so I had to reschedule it.
I sent them a note on that. They shouldn't. I'm sorry about that, Dylan. Uh,
So good.
they were supposed to call me back if there was a problem. They didn't call me back, so I assumed you'd gotten through. I should have asked them to call me back either way. That was stupid on my behalf. I'm sorry, but I got it done as soon as I got to work, but I guess they just didn't take it.
So good. Yeah, they said they had it, but they said it was labeled as starting tomorrow, so that I couldn't take it today. So
Gotcha. Sorry again, Dylan. Let me know if you have any problems. If you need more time to fit it in, like next week or something, I can give you an extension. Since that's my fault.
no, that's fine. I'm just thinking about taking it tomorrow evening.
Okay, that's cool.
Um, I did just a few minutes ago send you an image of a question that I had. If you had time, if we were able to go over it in class, that'd be great.
Okay, that's cool. I see it. Yeah, I got your notes about that. Sorry, I just saw your text too. I leave right at 3:30, so this must have came when I was on the road. So and as soon as I got home, I started prepping for class. The picture never came through. It does say, could we go over this, or is that the thing you sent me earlier? Uh, no, you'd already asked me about that. Yeah, I
Uh,
didn't get the picture.
oh, you didn't get the picture?
No, all I got was the text saying, could you go over this later in class? Or can you go over this, please? Yeah, yeah, feel free to send that this way by text or I don't think chat will let you do it, but if you can't send it to me chat and texting, just go ahead and send it to me an email and I'll find it. And we'll see if we can work it at the end of class or whatever.
Okay, yeah, I'll try and email it to you because it says it was sent through text, but it's just maybe being slow, but I'll send it
It
through.
might just be a delay. Mine will probably show up eventually then. Thanks. That's funny. All this time I've been picturing, hey, Jennifer, you have a question? Yes, ma'am.
Had sent you an email about it, but on the practice test for chapters 1 through 4, the practice test 03, only 4 questions are showing up.
Ah,
So you only have a chance to earn 10 points out of 100.
that's not helpful.
And I was relying on it to help me with my face-to-face.
Yeah. Yeah, I will fix that for you immediately. And I think what I'll probably do is well, actually you still got plenty of time, so shouldn't be a problem. But
Well, I had my test scheduled for tomorrow morning, so
oh, okay. Yeah, I'll get it right after actually let's see if I can fit it in right now. I think I can. Let's see. I know exactly what the problem is. One of the tests has been lost, which is aggravating. Let's see, edit. Yeah, it says it's worth 10 points. That's not helpful. Okay. That's a pain in my butt. So
I just went back to chapter practice to prepare.
yeah, no
Is that the
problem.
same questions?
It is the exact same bank,
Okay, good.
or except it's fewer banks because it's per chapter and the other one's got multiple chapters in it.
Well,
But
I was going through each one individually again, just to give myself the practice. I
gotcha.
don't test well, so all the practice I can get, the better.
Yeah, the more you take this, the definitely the better you'll feel and the better you'll do. I think I've got this set up now. For some reason it worked fine on the other one, but it didn't copy over in this class, so that was weird. All right, got more people coming in. Yay.
I just sent the image via email. If you
Okay.
can't go over it in class, I actually I'll have to leave a little early today. We have somewhere we have to go at 6:30.
Okay.
Um,
No problem,
I
Dylan.
just might try and get with you sometime during the week or maybe
Yeah.
next class to go over it.
Yeah, and I might even be able to answer it. It might be, I mean, I would still do it even if you're not here, and you'll have at least a version of it on the video at least. But yeah, I'll try to fit it into class. Actually, let me
Okay,
see if
cool.
my email comes up real quick. If that comes up, I might be able to do it now. Well, a lot of emails I get. Ah, there you go. I got it. Okay. Ah, yeah, I love this one. A 3 kilogram block sits on a 5 kilogram block, which is on a horizontal surface. Ah, so 3 kilogram, 5 kilogram. And all of a sudden, my favorite pen stopped writing. And 0.61 and 0.35. All right. So one of our students has a question. And actually, by not showing it, that'll prevent me from running into copyright issues. What I am going to do is copy a blank page and then go back and put it right here in front of this and paste the blank page. That is not it. And that's not it either. Paste page. Okay, there it is. So let me go ahead and I'm gonna go ahead and share my screen. That'll get us started. I don't have too much talking that I need to do a priority anyway, so we can just jump right into it. I will remind you guys that your test is due sometime this week. I sent it in this morning. I gave them today through Sunday. I did mess up Dylan, so if anybody needs Monday, I'm willing to go up to Monday of next week for y'all to take it. So just let me know if you need to take it during that period, and I can change it with the testing center. And that's just an exchange for it not being ready today. So let me go ahead and share my screen. I did fix your the other one though, Jennifer, so that should be ready to roll. Now I've got this.
Professor.
Yes.
So for the test scheduling,
Mhm.
so I just emailed the testing center. They replied back to me saying my appointment is set. I just said that I was with, physics 241 and then gave them my ID number. And then they're just like, okay, you're set. So they just know that the test and print it off
Yeah.
right then when I show
Yeah,
up.
when I turn that in for a whole class like this, I turn in the whole
Yeah.
roster, so they'll check your name against the roster when you get there. They usually require a photo ID, so make sure you bring
Yeah.
your photo ID, and you got an appointment. So it sounds like you're
Okay.
ready to roll.
All right, cool.
I told them that you can bring your own sheets, but anything that you bring, they're gonna have to scan and send to me. So it might be something where they might be better suited to print it out themselves for you or whatever, but whatever's, that's all going to be at the bottom of the test. So all those documents that you're allowed are there. But if you feel more comfortable with like a equation sheet that you made, that would be
Gotcha.
fine. Or if you printed out one of the equations with constants around it, that'd be fine too. Okay.
Okay, cool.
All right.
Did you just
Go ahead, Jennifer.
did you just say I could make my own equation sheet?
Uh, so here's the rule. You can make your own equation sheet, but if it has anything different than the one that's allowed, then it's going to cause you problems. So that's the only downside, but you can certainly copy the one that's there. Uh, the big thing is just it's not supposed to be any different. You're not supposed to have any words defining the equations or any of that kind of stuff. But yeah, if you want to write your own, that's fine. Or if you just want
If
to
I
print,
wanted to rearrange it, that's okay too.
yeah, that would be fine as well.
All right.
They're just going to have to scan it and send it to me, and
Okay.
that's not a big deal.
Okay.
Right. All right. So
Okay.
what we have here is a little corner of let's say the x-axis is like the floor, and the y-axis is like a vertical wall. The x-axis, in fact, has two boxes on it. One is 5.0 kilograms, and the other one is 3.5 kilograms, and they're connected via a pulley like this. Okay. The coefficient of static friction is 0.61, and the coefficient of kinetic friction is 0.35. And what they're wanting to solve for is, I'm assuming they want to know the acceleration. Oh, they want to know what force. So a 5 kilogram block is pulled to the right with a force of F as shown in figure 1. So what they have here is a force F. Can you see the other part of that question, Dylan? I'm looking at just, it stops at part A, so I assume it's asking us for what force would allow it to accelerate, what minimum
What
force.
is the minimum value of F needed to move the 2 blocks?
Okay, so F minimum. Okay, so that's the problem we're actually trying to solve. So what we got to do is draw free body diagrams. So first off, I'm going to draw the 3.5 kilogram blocks. What I have acting on it is M times G, which is 3.5 times 9.8, which gives me 34.3 newtons with 1 extra sig figs. I also have F normal acting on it. I also have acting on it a tension T, and I also have a friction force F that is acting between the 5 and the 3.5 kilogram object. And that should be the entire free body diagram for the 3.5 kilogram mass. Okay. So if I do the treating this as the positive x-axis and this is the positive y-axis, then I should be able to say that the summation of the forces in the x direction equals mass times acceleration in the x direction.
For block A, it is 3 kilogram, not 3.5. The 3.5,
Okay.
I think, is the kinetic coefficient.
That's what it was. Thank you. I appreciate that. That would have been a problem. So that's actually going to be 3.0 kilograms. Thank you. And that makes this a little easier too. And this one becomes 3, I think that's 27.4 or something. 29.4, that's what it is. So instead of 34.3, this becomes 29.4. Whoa. Okay, so the summation of forces in the x direction basically give us that F minus T is equal to 3.0 kilograms times A. I'll call that equation 1. The summation of the forces in the y direction equals mass times acceleration in the y direction. We're going to assume there's no bouncing or anything weird like that. So the acceleration in the y direction is automatically going to be 0. In that case, I'm going to get F normal, which points up, so that'll be positive, plus mg, which points down, so that'll be negative. So I'm just going to call it minus 29.4. But remember, you're adding the forces. That's the key point here. And that 29.4, of course, is just the m times g. And all of that's equal to 0. So that gives you equation 2. The normal force is equal to 29.4 newtons. Okay. Now we've got to do the same thing for the 5 kilogram mass, and that one's a little more complicated. So I'm going to say there's my 5 kilogram mass. Now I said the 3 kilogram going to the right was the positive direction, so that should mean the 5 kilogram going to the left is the positive direction. So I'm going to make the x-axis this way here. I didn't do that on purpose, but it's probably pretty helpful for you to see that it really doesn't matter. So what I'm going to do now is I'm going to say, first off, we've got mg acting on it. So this is mg, which is 5 times 9.8, and that gives me 49.0 newtons. We also have the normal force acting on it, but we also have the normal force for the 3 kilogram object, which I'm going to call now, I'm going to put a subscript 3 on it, and this will be a subscript 5. I think y'all can see why I'm doing that. Because guess what? Remember, the normal force on the 3 kilogram is actually applied by the 5 kilogram mass. So the 5 kilogram mass actually feels the normal force for the 3 kilogram mass as if it's pushing down on it. In fact, they're an action-reaction pair. So there's another force acting downward on it, and this force is F, or excuse me, not that F, is F in 3, which is equal to 29.4 newtons. Okay. It has a force acting on it this way that is F. And it also has acting on it a tension T that way. And let's see here. So we were arguing earlier that the friction force, did I make that right? I'm looking at the 3 kilogram. I got F minus T. It seems like I said the friction force was pulling it to the right. That's, I think that's good enough. And I considered that the positive direction. Okay, so that's all consistent. All right, so that works. I was just double checking to make sure that my friction force was acting the way I expected. So if I start pulling with that capital F on the 5 kilogram mass, that suggests the 5 kilogram mass is going to move to the left. Oops. Oh, the watch just fell off. Hold on a second. That suggests the 5 kilograms is going to move to the right. And the 3 kilograms is going to move to the left. So the 3 kilogram will feel a fraction of friction force pulling it to the right, which is how I drew it. So I was just double checking to make sure I got that right. Does that make sense to everyone? I haven't got all the forces yet. I have the normal force on object 5, the 5 kilogram object. I have the normal force on object 3 pushing down on the 5 kilogram object. I have the force that we're actually applying to the block, and I have the tension, but I also have a friction force between the ground and the 5 kilogram, or the floor and the 5 kilogram object. I'm trying to move the 5 kilogram object to the right. That would mean the friction force would act to the left. So I'm now going to add a friction force here, and that's the friction force of object 5. Okay, so that's the friction on object 5. But remember, when we say that the 3 kilogram object had a friction force pushing it to the right, basically what that meant is we have a friction force acting on the 5 kilogram object that's pulling it to the left. Let me double check that. So notice we got a 3 kilogram object on top. The 5 kilograms trying to move to the right. The 3 kilogram, therefore, is trying to move to the left. And the 5 kilograms is going to pull on it with a friction force to the right. That's the friction force due to on 3 due to 5. So the friction force on 5 due to 3 would be in the opposite direction. and that would be to the left. So now I'm going to add yet another force, and that's the friction sub 3. And that means I should go ahead and call this a 3 as well, and this a 3 as well, so we know what's going on. So it looks like I now have everything that's touching the 5 kilogram is the force F, the tension in the rope, the 3 kilogram mass on top of it applying FM3, the 5 normal force from the ground pushing up on it, the friction force from the 3, the friction force from the ground, and then the action at a distance thing is mg equals 49 newtons. So that seems to be like we have all the forces acting on it, and I think that should do it. So now I'm going to do the summation of forces in the x direction equals mass times acceleration in the x direction. So with this one, it looks to me like I got t plus f3 plus f5 minus f is equal to, and this guy, of course, was the 5.0 kilogram. So this is 5.0 kilograms times A. I'm going to call that equation 3. And now I have the summation forces in the y direction equals mass times acceleration in the y direction. And of course, again, we're going to assume nothing crazy is going on in the y direction, so the acceleration is going to be 0 there. In this case, that is Fn, that is Fn5 minus Fn3 minus 49.0 newtons is equal to 0. So with that in mind, we can say that Fn5 minus 29.4 newtons, that's Fn3, is equal to 49.0 newtons. So if I take 49 and add to it 29.4 by pulling it to the other side, I get Fn5 is equal to 78.4 newtons, and I'm going to call this 4. So now I've worked out the normal force for 5. Now we can go ahead and plug in the best case scenario. So what we're looking for here is F has to be just large enough to allow acceleration. So in some sense, we're going to be thinking we're going to set the acceleration in the x direction equal to 0, because we just barely want to have enough force for it to happen. So when we take that step, what we can see is that equation 1 is going to give us F3, which is 0.61, because it's a static friction. And I'm actually looking to the maximum force the static friction can put out. That's why I went ahead and used mu static times the normal force. So this is 0.61 times 29.4 newtons minus T is equal to 0. And that's just barely the largest force or the smallest force F that we can use to get that acceleration equal to 0. This tells us, in fact, that T is equal to 0.61 times 29.4. And that gives me 17.934 newtons. Now I can take equation 3, and that's going to be 17.934 newtons, okay, plus F3, which again, we're sort of peaking out here. So F3, the largest it can be, would be 0.61 times 29.4. and then F5, which would be 0.61 times normal force, which is 78.4 newtons, and then minus F is equal to 0. So from this, we should reach the conclusion that F is equal to, I'm going to take the 17.934 plus 0.61 times 29.4 plus 0.61 times 78.4. That gives me 83.692 newtons. It's a little dicey here in that you're doing addition, and remember when you do addition, sig figs get kind of turn out to be a pain in the butt. But I've got about 83 newtons. Do you recall what the right answer was, or do you not know that yet, Dylan?
84.
84. Well, that seems about right. I got 83.692. Does that make sense? This one's really, it's a nice problem. I love it, and it's one that I often put on our face-to-face tests or face-to-face midterms and final exams and that kind of thing, because it really makes you think about Newton's third law a lot and think about all the directions that things are acting.
There is a second part to that question where it says if the force is 10% greater than the answer you got for A, what is the acceleration of each block?
So in that case, all you got to do, I'll outline it rather than do the whole solution. What you're going to do is you're going to take that 83.692. You say F new is equal to 1.10 times 83.692 newtons. And times 1.1. And that gives me about 92.016. So what I would do is just assume that's going to be 92.0 newtons. For F, but you use it in all those same equations because the equations are all set up and ready to roll. The difference being now that A is not 0. So A is not 0. We know what F is, and mu's go to mu kinetic, which equals 0.35. So all you're going to do is everywhere you have that mu, like we just used, you're not going to use 0.61 anymore. You're going to use 0.35 and solve the system of equations that way. For A though, okay, you'd have to actually cancel out the two tensions in the two equations, because notice in one of them it's a minus t and the other one it's a plus t in equations 1 and 3. So if you add those two equations, that's automatically going to get rid of your tension and you'll be able to solve for the actual acceleration. That makes sense?
Yes, thank you.
If you have any problems with it, let me know. I can answer the other one, but I think it'd probably be better if you gave that a shot on your own. And then if that didn't work, you still didn't get the right answer, then ask me again or send me a text message. That'd be great. That was a big photo. I think that's why it didn't come through yet. It'll probably come through any minute now. Anybody have any questions on that problem? So yeah, that's kind of the most complicated one that I normally run into. That would be a test question. I normally don't ask as complicated test problems, but because this one appears over and over again in the bank, something just like it anyways, I do occasionally use that for test 1 or test 2 or test midterm or the final or something. So it is an often used problem. So definitely make sure you learn how to do that. Anybody else have any questions? All right, well, let's go ahead and start. Last time I introduced you to static friction and kinetic friction, and I also motivated you to do basically a derivation of centripetal acceleration. So I have a few topics I want to make sure you guys understand with regards to friction forces, and then I'm going to do a couple problems with regards to centripetal force. So let's go ahead and get started with this one. It says a 5-kilogram box can be pushed along a horizontal surface by a 200.0 Newton force directed at 36.9 degrees below horizontal. Alternatively, needs a comma in there. Alternatively, the box may be pulled along by a 200 Newton force at 36.9 degrees above horizontal. What is the normal force in each case? This is the main reason I'm actually doing this, is so you'd see how the normal force, we have now found two scenarios. When the surface is horizontal, we generally find that the normal force is mg. When the surface is tilted up at an angle theta, we normally find that the normal force is mg cosine theta. I'm going to show you now two cases where it's entirely different, and that's the whole purpose that I'm doing this. So solution, what we're going to make use of is static friction is less than or equal to mu static times F normal, and kinetic friction is equal to mu kinetic times F normal, and the summation of the forces is equal to mass times acceleration. We're making use of all that. So first thing I want you to think about is, in terms of this box, we should be looking at something like this, as if that's the box, okay? Now, the two scenarios are, we push downward on it like this, and this angle right here is 36.9 degrees, and this force is 200.0 newtons. Or alternatively, we could pull up on it where this angle is 36.9 degrees. So that's the two scenarios we're looking for. So I'm going to first take the pushing. So in the pushing example, what we're going to have, and I'm going to draw my coordinate system. Here's my x-axis. Here's my y-axis. What I'm going to do is I am going to have a normal force, F normal, which points in the positive y direction. So I made that actually green. And then I'm going to have this other crazy force that's not along any particular coordinate axis. And this angle, of course, allows us to get what the actual components are. It'll have a negative y component, so I'm going to make that red. And it will have a positive x component. So this is, and this is 200 newtons, by the way. Okay, so that's that force. And this, of course, is 36.9 degrees in there. Now we also have, acting in the downward direction, is the force mg. And that force, of course, is 50 times 9.8, which I think is 490. So, and that's right. So this is 490.0 newtons. 9.8 was supposed to be 3 sig figs. The 50 I used was 3. So we'll just say the 490 is sig or sig figs, but the 0 on the end is not after the decimal place. So we've got that. And now all we have is, we're trying to push the box forward. So we also have a friction force that's trying to fight that. And this, in this case, I'm going to say we're automatically putting enough force on it for it to move. That's why I'm only considering the kinetic friction. Okay. So when I do this, I can set up my summation of the forces in the X, or let's do the Y direction first. Equals mass times acceleration in the Y direction, which I'm going to call 0. So this is the key part that hopefully you guys are seeing. I'm going to say that we have F normal minus now 200.0 newtons times, we're trying to do the Y direction. So this is going to be sine of 36.9 degrees. And then we also have minus 490.0 newtons, and all that's equal to 0. So what we get is the normal force is equal to 490 plus, I should do the 200 times the sine of 36.9 first. And that'll give me 490.0 newtons plus I got 120.08 newtons. So that's what I got when I multiplied 200 times the sine of 36.9 degrees. That gave me the 120.08. I'm allowed to have 3 sig figs, so these two are not sig figs. I'm going to add this 120 to 490, and that's going to give me 610.1 newtons, and that's going to be part of the answer for A. Now for the pulling, we have sort of the same scenario. I'm again going to draw an X and Y coordinate system. We're still going to have a friction force that pulls back on it, only this time it might be a little better to draw it this way. So there's my friction force. I'm still going to have a normal force, of course. And that's my y-axis too, by the way. I should have labeled that. I didn't. Okay, so this my normal force, Fn. And then I'm going to have my pulling force, which I chose to draw like this. And this one again is 200.0 newtons at 36.9 degrees. You can see that it will have a positive X component. And in this case, it's actually going to have a positive Y component too. Now, we also have the mg, which is equal to 490.0 newtons. Okay. So again, we're just doing part A right now. That's why I haven't touched the X stuff, but the summation forces in the Y direction equals mass times acceleration in the Y direction. And that part's going to be equal to 0. That's going to give me, in fact, Fn minus 200, or excuse me, plus 200.0 newtons times the sine of 36.9 degrees, and then minus 490.0 newtons. That's all equal to 0. So you see that I had a Fn, I had the 200 newtons times the sine of 36.9, which points up, and then I had the 490.0, which points down. So that gives me F normal is equal to In this case, it's going to be 490 minus the 120. And in this case, I'm going to get 369.9 newtons is the normal force. So notice when we actually pulled it, the normal force was quite a bit smaller than when we pushed it. Was it because we were pulling as opposed to pushing, or was it something else that caused it? Anybody think they have an answer?
Fact that you're pushing down is giving it more downward force, which is increasing the friction.
Exactly. The table, because you're pushing down on it in addition to pushing it to the right, the table has to hold up its weight plus that downward component. So the normal force became larger when you were pushing it, not because you were pushing it, but because you had a component that was in the negative direction, in the negative Y direction. Does that make sense? And when you pulled it, again, it's not because you pulled, it's more because when you pulled it, you pulled up on it too. So you had, in that case, a force upward that the table didn't have to supply. So the normal force actually got smaller. Any questions on that? Now, if the coefficient of kinetic friction is 0.30, what would be the box's acceleration in each case? So now I'm going to go ahead and start working out the summation of the forces in the x direction equals mass times acceleration in the x direction. That's the only acceleration, so I can stop subscripting that. But what I am going to do is I'm going to say that 200.0 newtons times the cosine of 36.9 degrees. That's the actual little green vector in the pushing vector in the pushing diagram, and it points in the positive direction. That's why it's positive. And now I'm going to say minus 0.30. That's the kinetic coefficient of friction times the normal force, which is 610.1 newtons, like that. All of that has to be equal to, that's all the forces acting in the x direction, there's literally only two. All of that has to be equal to 50.0 kilograms times A. So A is going to be 200 times cosine 36.9. That's going to be 159.9 minus 0.3 times 610.1. That's going to be minus 183.0 newtons. And then all that has to be divided by 50.0 kilograms. When I take 159.9 minus 183.0, I get 23.1 negative. So what we've discovered here is that the friction force is actually quite a bit larger than the 200 newtons that we're going to actually apply. So I literally had started this problem with 100 newtons, is one that I just made up. And I said, nah, that might be too small. I better be careful. So I made it 200. And the fact that we got a negative tells me already that that was still not big enough. I probably should have used 300 newtons or something like that. The problem is because the force that I'm applying is at an angle. If I increase that magnitude, I also increase the magnitude of the downward component too. So this one's just not going to move basically. So I've screwed this problem up in terms of being able to work out the numbers. But in principle, you see exactly how it was done. That would basically be the acceleration. So if I divided 23.1 by 50, that would give me negative 0.462. But that's literally imagining that friction just on its own got strong enough to push the thing to the left. Okay. What really is going to happen is it's going to sit perfectly still. And in fact, the fact that the coefficient of static friction is larger tells you that you're really going to be sub or way below the force that you need to break the motion loose to actually get it from not moving to move. So I'll just leave it at that and say this will not move at all. Okay, but that's for pushing. So I didn't mean to teach you that part, but it works out okay. We can see literally in this case that you are actually not going to be able to move it at all. But in the other case, we should be able to. So I'm going to do that one now. So the summation of the forces in the x direction equals mass times acceleration in the x direction. In this case, what I'm going to have is the 200 newtons. I'll try to wiggle a little line here to keep these separate. Like that. Okay. And now I can erase that little line here. That'll make it a little bit easier. So what I'm going to do now is I'm going to put the force in there, which is 200.0 newtons times the cosine of 36.9 degrees minus 0.30 times 369. So let's say 369.9 newtons is what goes in here. And all that's going to be equal to 50.0 kilograms times A. So hopefully when I do 200 cosine 36.9, I get a bigger number than 0.3 times 369. So let's check that out. 200 times cosine 36.9. I don't know why I did that again. I already knew it was 159. But anyways, here we are. So 159.9 newtons minus 0.3 times 369.9 gives me, all right, finally, 110, actually 111.0. Is equal to 50.0 kilograms times A. So in this case, I'm going to get A 159.9 minus 111.0 gives me 48.9 divided by 50.0 kilograms. That's 2 sig figs divided by 3 sig figs. So this is 0.978 meters per second every second. That's the acceleration. Any questions on that? Okay. So yeah, this problem was totally meant for you to see that, in fact, when you have other forces acting on it that might be acting in the plus or minus y direction, the normal force can actually become quite a bit different from mg or mg cosine theta. Sometimes the friction force, the normal force can get larger. That's when something else is pushing down on the object. And then there's other times the normal force can get smaller, and that's when the other force is actually lifting up on the object, doing some of the table's work. So hopefully that was fairly instructive. Anybody have any questions on that one? Okay. So just remember that second part of part B, the first part that we did in part B, that one was basically the problem was we just made the force. I made the force too small, or I made the angle too big, or something like that, because basically I made it where the friction force was larger in magnitude than the horizontal component of the force we applied. And whenever that comes up, if you actually set up your coordinate system for, let's say a positive or a negative sign, if it's going the way you get it, if you get the opposite sign, that's an indicator that you possibly screwed something up, or it might just be that the force wasn't big enough to do it. Friction always is the kind of force that only gets as big as it needs to be and no bigger. The best example you can see of that is the first example in this book. They basically say here's a freight of 50 kilograms. What is the static friction force if you push to the right on it with a force of 0 newtons? And then they do 20 newtons, and then they do 38 newtons, and then they do 40 newtons. And then they say, what's the acceleration if you actually push it with 50 newtons or something like that? But in that case, you can see what happens when the force is 0, the friction force is 0 as well, because it doesn't have to do anything to try to prevent it from moving. When the force is 20 newtons, as long as that 20 newtons is smaller than mu k times the normal force, then it's going to just make that big a force, period. So it'll make a 20 Newton force. The same thing happens with the 38 newtons. It turns out the 38 newtons is smaller than mu k times the normal force. So the friction force is going to meet the demand and basically apply a force of 38 newtons. And then finally, when you do the 41 exceeds the normal force, or excuse me, the normal or static friction. So that becomes a kinetic friction problem. And then you're going to use the kinetic coefficient of friction instead of the static, and you can calculate the acceleration from it. Okay. So definitely check out that example, but that was the main thing I wanted you to see. This page is awful. Moving it to the trash. Yes. I didn't know where that crazy page came from. Okay, so now we're going to do another one. In this case, I'm going to try to use numbers, and I'm specifically going to try to use numbers that are helpful and easy to do. So what I'm going to do is use numbers from basically not unlike the numbers we have in the textbook. I'll double check on that example, by the way, while I'm here. So the example I was telling you about with the various forces, so you can understand the normal force or the kinetic and static friction. Yeah, it's example 5.1. So example 5.1, friction, static, and kinetic. I highly recommend you doing that. I think that's better for you to just do that on your own and see it and read it. Ask me questions if you have it, but you shouldn't. It should be pretty straightforward. If you do, it's not a big deal. So I'm going to skip the wall and the box problem. That's kind of nice. But what I want to jump to is something like a problem that your book does. So what we're going to do is we're going to imagine a tabletop. And then, of course, mounted on that tabletop will be a pulley. And then on top of that tabletop will be a mass. And that rope, notice the rope is running parallel to the tabletop. If it was up, we'd have to adjust the normal force. If it was down, we'd have to adjust the normal force as well. But let's say this mass is 50.0 kilograms. And let's say this mass right here is 20.0 kilograms. Okay. Now that's what we're wanting here. And what we're going to do is we're going to say that the kinetic coefficient of friction, mu k, is equal to 0.20. And what we'd like to know is find out what is the actual acceleration. So A equals question mark. So now that I'm going to do this, I want to make up a free body diagram for each of them. So let's say solution. I'm going to first off draw a free body diagram for the 50 kilogram mass. And that's going to be my y-axis. This is going to be my x-axis. I'm going on the assumption, since this tabletop is actually horizontal, I think the 20 kilograms should be more than enough to slide it off, but we're going to have to find out for sure. So I'm choosing to call the right, and anything that makes the 50 kilogram box move to the right is going to be the positive direction. That means when we go to the other one, down is going to be the positive direction. Okay, so the forces acting on the 50 kilogram block, our box, is its normal force, F normal, and that acts upward. There's going to be a tension force, T, that points in what I call the positive direction, so that's just FT. And then there's going to be a negative force that is mg equals 490.0 newtons. And they specifically gave us a kinetic friction. So we're assuming that the friction is going to be, or the force is going to be so large that the static friction will easily be overcome. And then we'll just be pulling against a static friction force. And that static friction force points in the negative direction, and it's right here. And we're going to make use of the fact that the static friction, or excuse me, the kinetic friction is equal to mu kinetic times the normal force. We're also going to make use, of course, that of the summation of the forces is equal to mass times acceleration. Now I'm going to draw a free body diagram for the 20 kilogram mass. This one was for the 50 kilogram. So now what I'm going to do is say this is my positive x direction. This is 20.0 kilograms. The forces I have acting on it are 198 newtons. That's acting in the positive direction. And this is mg is equal to 20 times 9.8. 2 times 9.8 is 19.6. So this should be 196 newtons. Now we also have acting on it a tension T that way. Okay. The pulley is supposed to be frictionless and massless, so that's why the two tensions aren't different. We're also assuming the string's not going to get slack, nor is it going to stretch. So if we move 1 inch, they both move 1 inch. If we move 1 inch in 1 second, they both move 1 inch in 1 second. And if we move 1 inch in 1 second and then 2 inches in the next second, the same is going to happen to the other. So we see the accelerations are all the same, all that good stuff. So now I'm going to write our equations of motion, which is Newton's second law. So the summation of forces in the y direction equals mass times acceleration in the y direction. For this guy that we've already drawn, that's going to be the normal force Fn minus 490.0 newtons has got to equal 0. So that gives us 1. The normal force is equal to 490.0 newtons. Now I'm going to do the summation of the forces in the x direction equals mass times acceleration in the x direction. So in this case, In this case, I'm going to see T minus, now I'm going to go ahead and write 0.20 times 490.0 newtons, because mu K, or excuse me, the friction force is mu K times the normal force. And all of that has to be equal to 50.0 kilograms times A, and I'm going to call this equation 2. Now I have the summation of the forces in the x direction equals mass times acceleration in the x direction. In this case, I get 196.0 newtons minus T is equal to 20.0 kilograms times A. This is going to be equation 3. Okay. So I'm going to add 2 and 3. And when you do that, you can see that I'm going to get let's do what 0.2 times 490 is. That should be 49 times 2. That should be 98. So I think it's going to be 98. Yep, 98 it is. So this guy can also be written as T minus 98.00 newtons is equal to 50.0 kilograms times A. When I add these, I get T minus 98.00 newtons plus the left-hand side from equation 3, which is 196.0 newtons minus T is equal to 50.0 kilograms times A plus 20.0 kilograms times A. You can see that the T and the minus T cancel out. And now all we have is 98 taken away from 196, which would be 98. So now I'm going to get 98.00 newtons is equal to 50. Notice there's a common factor of A, so I can add the 50 and the 20 to get 70 kilograms times A. So this will give us A is equal to 98.00 newtons divided by 70.0 kilograms. So 98 divided by 70 gives me 1.4 meters per second every second. And that's the acceleration. Does that make sense to everyone? All right. So now that we have that, we can go back. I'm going to go back into equation 2 and solve for T. So let's call this 4. So plug 4 into 2 and solve for T. So now I can say T minus 98.00 newtons is equal to 50.0 kilograms times 1.400 meters per second every second. And this gives me T, I'm going to say 1.4 times 50. And then I'm going to add 98 to that. That gave me 70. So plus 98. That should give me 168. So the tension should be 168.0. And by the way, when I multiply 50 times 1.4, both of those have 3 sig figs. That gives me 70. So that's good to 1 decimal place. So lo and behold, I get 4 sig figs on this guy. So that's what the tension is. Anybody have any questions on that one? All right. So that's another good example of how you use it. Now I want to show you one more where you actually have to be a little more careful. So what we're going to try to do here is we're going to set up an inclined plane problem where we're going to try to figure out what weights must be hanging such that the mass on the incline can stay perfectly still. So I'm going to take and imagine a mass sitting on an inclined plane. So let's do this. So that's a mass sitting on an inclined plane. And I'm going to say this angle right here, theta, is equal to 36 point, I think it's 87 is what I normally like to use. I'm going to say 36.9. I think 3 sig figs is probably pretty good. And what I'm going to do over here is I'm going to put a mass on it, and that mass is 10.0 kilograms. And now I'm going to run this rope over a pulley, and the pulley is going to be set up so that the rope runs parallel to the top. And then there's going to be a mass hanging over here, and this mass I'm just going to call M. Okay. What I'm also going to do, though, is I'm going on the assumption that the static coefficient of friction, mu static, is equal to 0.40, whereas the kinetic coefficient of friction, mu kinetic, is equal to 0.30. Okay. What I want to know is what range of M allows the system to not accelerate. Okay. So I'm going to go ahead and start with the free body diagram. So there's my x-axis. There's my y-axis. This is my 10.0 kilogram mass. I have acting on it a tension T. Now, what we're trying to do is figure out the smallest mass that'll keep the thing from sliding down the incline in this particular one. I got to do that. Then I got to figure out what maximum mass is allowed such that it won't slide up the incline. So that's the next part. But right now we're just doing the free body diagrams. I also have a normal force Fn acting that way. I also have a non-broken down force whose magnitude is m times g. So this is 98.0 newtons acting downward like that. Now that is consistent with a negative y component and a negative x component. And we know that if this angle is 36.9 degrees, this one is 2. Okay. So this one would be 98.0 newtons times the sine of 36.9 degrees. And that equals 58.84 newtons. And then this one's going to be 98.0 newtons times the cosine of 36.9 degrees. And that gives me 78.37 newtons. Okay. Now, in addition to that, what we can use is the mass M is going to be trying to possibly pull it up the incline if it's big enough, or if it's too small, it's going to allow it to slide down the incline. What we're trying to do is try to find out minimally what mass I have to put on the other side to keep it from sliding down. So when I do that, I'm going to say to find the minimum force, I'm going to use a friction force F here for smallest M. Okay. Now later we're going to try to figure out a M that's big enough to keep it, from sliding down, but it's not big enough to allow it to go up, in which case the friction force is going to be acting the opposite way. So I'll put right over here, this is the friction, this is for M max. In other words, what's the maximum force we can have before it starts to move? Okay. Now I also need a free body diagram for the hanging mass. And I've chosen up as the positive X direction. So I'm going to choose down over here as the positive X direction. And this is a mass M. And in fact, we have a force that's just mg that way. And then we have another force that's just the tension this way. So when I go to compute, let's say the summation, put it back in black. Let's do the summation forces in the X direction equals mass times acceleration in the X direction. That's going to give me mg minus t is equal to just ma. Okay. Now I have to do the summation of the forces in the y direction equals mass times acceleration in the y direction for the incline. So again, the A is going to be equal to 0 here. And right now I'm going to say to find smallest M. So when I try to find the smallest M, I'm going on the assumption that the F is helping me hold it up the incline. So I'm using the green F arrow. But in this case, we've got to do the summation of the forces in the y direction, which is the normal force minus 78.37 newtons is equal to 0. So the normal force is equal to 78.37 newtons. I'm going to call that equation 2. Now I've got to do the summation of the forces in the X direction equals mass times acceleration in the X direction. In this case, I'm going to say T is the positive force plus we're going to actually consider the maximal force that the kinetic or that the static friction can be. So I'm going to go ahead and say this is mu K, or excuse me, mu S times 78.37 newtons. That's the friction force. And then we have minus the 58.84 newtons. And all that has to be equal to, this case, it's 10 kilograms. Times A. Okay. So in this case, if we allow a to equal 0, then we get 1 becoming t is equal to mg. And then for 2, or excuse me, for equation 3, not that one. I should have numbered this 3 as well. So let's erase that 2 and put a 3 here. Well, let's just erase everything because we can do that. Okay, so now I'm going to take equation 3, which is t plus mu static is 0.40 times 78.37 newtons minus 58.84 newtons is equal to 0. Now we can combine those two. And what we get is mg plus now 0.4 times 78.37 gives me 31.35 minus 58.84 newtons is equal to 0. So this gives us that m should be equal to 58.84 newtons minus 31.35 newtons. All that divided by 9.80 meters per second every second. So 58.84 minus 31.35 gives me 27.49 divided by 9.80. And that gives me 2.805 kilograms. So that's the minimum mass that we can use to keep it from sliding down the incline. I'm going to put this as min. Any questions on that one? Now we can do more or less the same thing with this for the other one, but now we've got to interpret it as we're looking for a mass that's obviously bigger than 2.8 kilograms because we don't want it to slide down the incline, but we also don't want it to be so big that it makes it slide up the incline. So in this case, we're going to use the friction force to pull down the incline, and therefore we're going to use the red arrows for the friction. So now I'm going to say to find the largest M. So in this case, what we're going to have is we're going to allow the same forces that we had before. And now we're going to imagine A equals 0. So if we assume A equals 0 and F static equals F static max, which is what we did before, okay, then equation 1 will become mg minus t is equal to 0. And equation 2 will now become, we still have the tension pointing up the incline, but now we're going to have the friction force pointing down the incline. So it's going to be minus, notice before that we actually computed this 0.4 times 78.37. And from that, we got 31.35. So I'm going to use that again. So I'm going to say minus 31.35 newtons. That's the friction force. And notice it's the opposite direction as T. So that's why it has a negative. And it's not like the green one, which would have had the same sign as T. Now we also have the 58.84. So I'll say minus 58.84 newtons. And all that's going to be equal to just plain 0 because we just want it to barely be the case. So now I can combine them and I get mg minus 31.35 newtons minus 58.84 newtons is equal to 0. And that gives me m, and I'll call this m max, is equal to 58.84 plus 31.35. That's going to give me 90.19 newtons on the top. And then I got to divide that by 9.80 meters per second every second. And that gives me 9.203 kilograms equals m max. So what we discovered is as long as this hanging mass is no bigger than 9.20 and no smaller than 2.81, then it shouldn't move. Any questions on that? All right, so that's enough. We've actually run out of time anyway, so I'm going to go ahead and call it. Next time, we will meet. Remember, you just have a test that's supposed to be done sometime today up through Sunday. Again, as I told you guys, I will allow you to go up to Monday, just because I missed today for my own problems. So if y'all need an extra day, you're welcome to wait until Monday to take it, but I would advise you to take it sooner rather than later. So y'all have a good one. Make sure you chat me your first and last name so I'll have it for the roll. But other than that, you're good to go.
Sir,
Yes.
I know we talked about me being able to take the test with ROTC. I was wondering how to get them in contact with you so that they can have, like, so that you can see who's proctoring.
Gotcha. Are you ROTC like over at Regent?
I go to Regent, but our ROTC is through ODU.
Oh, gotcha. Okay, so you're in the area. Is there any reason why you couldn't do the testing center? Is it just because your duties or whatever you had?
So I'm at ROTC like all day, and then at night my sister just had a baby, so I'm trying to help her out while her husband's working nights.
Gotcha. So yeah, we can do the ROTC. You can give them my personal cell phone number. And if whoever's above you that can actually proctor your test, I just need them to basically sign off on some questionnaire of what they're going to do during you taking the test. In other words, they got to watch you the whole time. They got to make sure you don't, go on the internet and that sort of thing, other than for the test. So if they just contact me via text, I'll probably ask them for their email and I'll send them a form and we'll have it set up that way.
All right, sounds good. Thank you.
Okay. All right. See you, Josh.
See ya.
Anybody else have questions? Let's see, Mark and Andrew and Tracy, Ronnie, Johnny, Mickey, and Mike. No question on A's? All right, Andrew, you're good. All right. You guys are free to go. Thanks again, everyone. Tracy, do you have a question, or Mark? It's like y'all aren't.
Mark.
It's Mark. Gotcha.
Mhm.
Okay, I'm barely hearing you. That was the problem. Mark, you have a question then? You're from a 202 class. Is that Mark, right?
Yes.
Okay. Let me stop sharing here. And I do have some time I can spend with you. So what's up?
So it's another practice test problem. Like, let me try to find it again.
Okay. And you can share your screen. I've got it set where you're allowed to do that now.
Okay, okay. Yeah. Oh no, my paper. It's this problem right here. I
Okay.
thought it would want us to use Coulomb law, which is F equal K times Q1 over Q1 Q2 over R squared.
Mm-hmm.
And we try to find Q. So like I did that. I isolated Q, but like I don't see my answer up there. So like, do you want me to type it down in
Okay.
chat to show you the process, or?
Now let me sort of play out what you got here. So I'm looking at it says two 10-cent coins, dimes, carrying identical charges are 2.5 meters apart on a table. If each of these experiences an electrostatic force of magnitude 2 newtons due to the other coin, how large is the charge on each? Okay. So what you should have here is K times Q squared, and you just leave it as K and leave it as Q because you don't know those numbers yet, and there's no reason to actually put in the K because it's going to cancel out on both sides in some sense. So you're going to have K times Q squared over 2.5 squared is equal to just 2. Is that what you remember doing?
Yes, it was something like this.
Okay.
But the thing is, when I tried that, I don't think I still got the right answer.
Okay, so let me check it real quick. I'm going to do my calculations, see what I get. So first off, I'm taking 2.5 meters and I'm squaring it, multiplying it by 2. So 2.5 squared times 2, and that's from the 2 newtons that it already was. And now I'm taking that and dividing it by K. So I divide that by 8.998 times 10 to the 9th. Okay. And now I got to take the square root of that. Did you remember to take the square root?
Yeah, I did that earlier as well, but like I got 3.710
Okay.
e to the negative 5, but I don't think I see anything like that up there.
I got
that
point
makes-
0.001234 Yeah, I got 3.7 times 10 to the negative fifth, which could be like 37. How large is the charge on each coin? Each of these coins experiences an electrostatic force of magnitude. Okay, so they're repelling each other. Yeah, I'd call that 37 microcoulombs. And none of these are really right.
Yeah.
So magnitude, how large is it? I think this has got an error in it. I don't know how I haven't found it before because I've been using these banks for a long time. Oh, they did ask you to use 9 times 10 to the ninth. Let me try that and see if that works any better. So 12.5. see. That's still the same thing. Hearing identical charges. Yeah, I would say this is a problem with the actual question. I'm going to have to repair it or erase it. So yeah, you did it absolutely right.
Oh, okay. And then I got some more in
Okay.
my 7th attempt. Let's see which. Yeah, this one. I could have sworn
7
it
or
was
6. That one.
I guess all 3 of these.
Okay.
So this one is, so proton is located at x equal 1.0 nanometers,
Uh-huh.
and electron is pointed upward at 4.0 nanometers. Find the magnitude of the electric
Static force.
static force.
Each one exerts on the other. Yeah. Okay. So what they've told you is the electron is at x equals 0, y equals 4.0 nanometers, and the proton is at x equal 1 nanometer and y equals 0. So if you drew that on a coordinate system, you'd see that you could basically use the Pythagorean theorem to find the whole distance between them.
Yes, and I did that, and I got,
Okay.
what was that? I think it was this 7.07 times 10 to the negative 5.
Let's double check. So you got 4.12 is what the distance you got?
My distance, I got 7.07 times 10 to the negative 5. This is 1 nanometer, and this is 4 nanometer.
Oh yeah, I was still in nanometers, but you should have had like 4.12 nanometers. I'm wondering, maybe I'm looking at it wrong. I've got a proton at x equals 0, 1, y equals 0, so that's right there. So it's 1 nanometer to the right of the origin, and then the electron is 4 nanometers up from the origin.
Yes,
So that
that's,
should be 1 squared plus 4 squared square root.
yes, I think that's what I'm did.
Yeah. So that's about 17. Okay, so we can use it that way. And what they want to know is the magnitude of electrostatic force. Okay, so that's going to be 9 or 8.99. Actually, they told us to use 9, didn't they? So 9 times 10 to the 9th times 1.602 and 10 to the negative 19th. I'm going to square that. So that's kq squared divided by 7. I'm going to do 17 times 10 to the negative 9. Whoa, no, I'm going to do I do want to do that. Let's see, 4 point. Try something quick. I'm going to say 4.123 times 10 to the negative 9. Okay, so I did that times that. Parenthesis squared. And I got 1.35 times 10 to the negative, or 1.4 times 10 to the negative 11th. Yeah, that's the one I got.
Oh, that's an answer. Okay, so what did I do wrong then?
Did you remember to square the 1.602 times 10 to the 19th?
Yes, this is basically squaring times itself. 1.6 times 10 to the negative 19
Mm-hmm.
times itself.
Times k, and then did you remember to square the distance in the bottom?
No.
That might be.
Oh, wait, no, I still got a real answer.
Yeah, I think what's wrong when you told me your distance, that didn't seem right, because it should be, like I said, 1 nanometer to the right, 4 nanometers up. So
Yes.
the distance between them should be the square root of 1 squared plus 4 squared. That's the square root of 17, which is 4.123. So 4.123 nanometers is the separation for them. So you can put that in as 4.123 times 10 to the negative 9th, and then square that. And that's what I got, 1.35 times 10 to the negative 11.
Okay, yeah, I got it now. I just forgot to square the
radius, or the distance.
yes.
Yep.
Okay, that's how you get it.
I'm looking at 7 now. Or you want me to look at 8 instead?
Can you do 7?
Okay, yeah, I'll do 7. So a 5 microcoulomb point charge is 12 centimeters from a negative 5 microcoulomb point charge. What is the magnitude of electric field they produce at a point on the line connecting them where their electric potential relative to infinity is 0? Okay, so in this case, what is the magnitude of electric field they produce at the point on the line connecting them where the electric, okay, so do you know when they're saying electric potential is 0, that's the KQ over R?
Mm-hmm. Okay.
So that position would be basically dead center between them at the 6 centimeter mark.
So R is equal to 6 centimeters since it's the halfway point.
Mm-hmm. Now you're going to use the two electric fields due to the positive charge, which we'll say pretends to the left, and the negative charge, which will pretend to the right. If you go dead center between them, the positive charge is going to cause an electric field pointing to the right, and the negative charge is going to cause one pointing to the right. So you really just have to calculate the magnitude and multiply it by 2.
Okay, so should be 9.6 K times
10 to the negative 6.
times
That's the micro
5.0 times 10 to the negative
squared
6
times 9
square
10 to the 9 divided by 0.06 squared.
Wait, did I mess up? I feel like I messed up. So F equal 9.0 e to the 9 times Q, which is 5.0 microcoulombs divided by R squared, which is 6 centimeters, so 0.
I got the 25 meganewtons per coulomb, the last answer down there. What did you get? Did you actually get 0, or were you just taking a guess because you didn't really understand the question?
I think I misclicked there.
Okay. So what's going on here is the voltage formula. That's the one formula I told you where it's really smart to make sure you put in the sign of the charge. That's the only way, for instance, in this case, that you can get that the electric potential is 0 at the middle. So once you realize that, then you'll quickly realize that 6 centimeters is the distance away from each of them, where you get the V is 0. Then you calculate the electric field, which is K times Q over 6 centimeters squared, but in meters. And that's the electric field due to one of them. They point in the same direction. So you multiply that by 2. And instead of the 12.5 meganewtons per coulomb, which is what you get when you just do one calculation, you get twice that, which is 25 meganewtons per coulomb. Did that throw you, or was that helpful?
I understand you. I just feel like I'm writing this down wrong.
Gotcha.
So this is what I have so far. So K times Q over R square give me 12. How many numbers is that? 12.
Yeah, everything you got there, that's exactly right. That's the number, but you need to multiply that number times 2, not times itself.
Whoops. Oh. Oh, okay. I don't know what I was thinking when I was growing up.
Yeah. Yeah. So the force should be the same in both cases. So you end up getting the 25 million. But yeah, that's exactly what it should turn out to be. You did everything right there. Does that make sense?
Yeah, okay, I get you. I was just like being stupid and just times it by itself. And this one, I didn't get a chance to get started on this, I think. So
Okay, so the one thing that we know about this, I'll give you a big hint. This is something that you can also use. For a parallel plate capacitor, we discovered that the electric field between them is sigma, which is the surface charge density, divided by epsilon naught. So when they tell you to find out the surface density, they're asking you for sigma.
Sigma.
The sigma is well, it's just a surface charge density that we talked about a little bit in class. I'll tell you what, let me steal the page real quick and put up something on my screen.
Okay.
Okay. So what I'm going to do is on my screen, I'm going to remind you that for a parallel plate capacitor, as soon as this comes in, for a parallel plate capacitor, C is equal to epsilon 0 A over D. That's just remembering that it's that case, epsilon 0 A over D, if it's air filled or it's vacuum filled. Okay. We also know that the electric field in the capacitor is sigma over epsilon naught. I showed you that in class, but basically that's the actual electric field. We also know that the voltage is equal to the electric field times the distance for the capacitor. And we know that C is equal to Q over V. So you can use all these things combined to some extent. I think it gave you the area. Is that right in the problem? Did they give you the area in like square meters?
Yes, they give me the area. It's 0.020 m squared. So 0.00. So that would be 20 centimeters square, I believe.
Okay, so 0 what squared?
0.020 m squared.
Okay, gotcha. Like that. So that's our area. Did they give you a separation between the plates?
Yes, 0.90 millimeter. So that's D.
0.90 times 10 to the negative third meters. That's D. Okay. What else? What's the other information they gave you? I'm not looking at it right now.
The electric field is 2.1 times 10 to the 6 N over C.
2.1 times 10 to the 6 newtons per coulomb.
Yep.
Okay, so we're actually in a pretty good space now. Just with that electric field alone, you can automatically figure it out, but I'm trying to figure out if there's a way they're wanting you to use it without that, because that is something that you're unable to derive yourself, but we do it in our calculus-based class all the time. So what we can say is C is equal to Q over V, and V is equal to E over D. And then we can say epsilon 0 A over D is equal to Q over E D. And sigma that they're asking for is supposed to be Q divided by A. So we can now take and pull the A to the right-hand side, multiply by ED on both sides. So I'll get epsilon 0 ED over D is equal to Q over A. You can see the E's cancel out, and that should be basically it. This is the surface charge.
Okay, hold on.
So I got 1.8 times 10 to the negative fifth. Of course, you can also multiply this number times 10 and divide this number by 10. And then that would give you 18.59 times 10 to the negative 6 coulombs per meter squared, which is 18.59 microcoulombs per meter squared. I don't remember what the answers were, but that should be one of the answers.
Yes, there's a 19 microcoulombs.
Yep. 19 microcoulombs should be it. Oh, wait a second. Is it giving you 19 microcoulombs, or is it giving you 19 microcoulombs per meter squared?
Per meter squares.
Okay, good.
And
And that should be it. And looks like my supper's ready. So you can come by again tomorrow if you'd like. I got to get out of here though. So any more quick questions before I split, dude?
no, I'm gonna do the test today. So
Okay, good luck.
thank you. Have a good day, Professor.
Oh, you're doing it today or tomorrow?
Today, the test is due today, the online test.
Oh, the online. Okay, gotcha. Yeah, yeah. Whew, I thought you were about the face-to-face test. All right.
No.
See ya. Have a good one, bud.
Thank you, Professor. Thank you.
You're welcome. Tracy, you're not here still, are you? You can send me a chat if you are. In case you have any questions. I think you're gone. All right. Bye, everybody.